Quantum generative models are frequently touted as the next breakthrough for medical imaging, especially when labeled data is scarce. But how do we actually verify those claims? In this video, we're breaking down a rigorous new benchmark that puts quantum latent GANs head-to-head with classical counterparts for brain MRI augmentation. The results challenge a lot of assumptions in quantum machine learning, and they highlight exactly why controlled evaluation matters. If you've read recent papers on quantum GANs for medical imaging, you've probably seen accuracy improvements reported. But look closer at the methodology. Most of these studies rely on a single training run, compare a quantum generator against a classical baseline with a completely different parameter count, and evaluate augmentation at only one dataset size. That leaves a massive gap. We don't know if the quantum component is actually doing anything special, or if we're just looking at noise, capacity differences, or statistical flukes. So the real question is this. When you control for parameter budget, random initialization, and data regime, does a quantum latent generator actually contribute beyond a classical one? To answer this, the authors designed a tightly controlled benchmark. The pipeline starts with a convolutional variational autoencoder. Grayscale brain MRIs are resized to 128 by 128 and encoded into a 16-dimensional latent space. The VAE uses a callback labeler regularization term to pull the aggregated posterior toward a standard normal prior. They set the beta coefficient to 1,000, which is low enough to preserve reconstruction fidelity while still enforcing a smooth, continuous latent manifold. Once the latent space is learned, they train a conditional Wasserstein GAN with gradient penalty. This is crucial for stable adversarial training. The critic is a layer norm MLP that estimates the Earth mover distance, and the gradient penalty enforces a one-Lipschitz constraint, preventing the critic from becoming too steep and destabilizing the generator. The generator is conditioned on the tumor class label, ensuring that synthetic samples match the target diagnostic category. Now here's where the benchmark gets interesting. The generator is trained in one of two configurations. The quantum arm uses a 4-qubit variational circuit with a depth of 2. Input data is encoded via single-qubit Ri rotations, followed by a trainable block of Ri and RZ rotations, interleaved with a ring of CNOT entanglers. The circuit prepares a state, and then 4 poly-Z expectation values are measured. Those 4 bounded outputs are concatenated with a class embedding, and pass through a classical readout head to produce the 16-dimensional latent code. The classical arm is structurally identical in every way except the quantum circuit. Instead of measurement expectations, it takes 4-dimensional Gaussian noise as input, and the exact same classical head maps it to the latent space. The parameter counts are nearly identical, 1,648 for the quantum generator and 1,632 for the classical one. The critic has about 13,000 parameters. By matching the generator capacity so closely, any performance difference can't be chalked up to model size. The synthetic latents are decoded back into images and used to augment a pretrained ResNet 18 classifier. They sweep across labeled data fractions from 5% to 100%, evaluating over 8 random seeds. They use paired t-tests with Hom-Bonferroni correction for multiple comparisons, and they don't just look at downstream accuracy. They also measure intraset diversity using pairwise structural similarity index and per pixel standard deviation. Plus, they visualize latent distribution overlap with t-SNE. So what did they find? Across every data fraction, no augmentation variant significantly outperformed training on real data alone. The quantum and classical generators are statistically indistinguishable. The only near-significant difference appeared at 25% data, where the classical generator actually degraded performance slightly, but that didn't survive multiple comparison correction. More importantly, they analyzed generation quality. At 5 and 10% data, both generators produce highly similar blurry samples. Pairwise SSIM sits around 95 to 98%, and pixel standard deviation is extremely low. That's a textbook signature of mode collapse. As data increases to 25 and 100%, diversity improves, and structural features like skull boundaries and internal textures emerge. But even at full data, the quantum generator is consistently less diverse than the classical one. The t-SNE plots show that at low data fractions, synthetic codes form regions largely disjoint from the real data distribution. The generated samples are off distribution precisely where you'd want them to help most. Why does the quantum model fail to pull ahead? There are 3 structural reasons. First, the quantum circuit only outputs 4 bounded expectation values. The classical readout head carries the vast majority of the modeling burden, and mapping 4 noise dimensions to a 16-dimensional latent code is straightforward for a small, fully connected network. The quantum component essentially acts as an alternative low-dimensional noise source, not a generator of richer correlations. Second, a depth 2 4-qubit circuit has severely limited expressivity. Entanglement across just 4 qubits in a shallow ansatze doesn't provide enough representational power to outperform a matched classical head. And third, deeper circuits would likely run into barren plateaus, where gradients vanish exponentially with qubit count, making optimization practically impossible. Finally, operating in a learned latent space decouples the generator from pixel-level structure. Any potential quantum inductive bias gets diluted by the VAE decoder. This benchmark highlights a critical issue in quantum machine learning research. Uncontrolled protocols easily produce apparent quantum advantages. A single favorable seed at 10% or an uncorrected comparison at 25% could easily be misinterpreted as a breakthrough. But when you match parameters, sweep the data regime, average over seeds, and actually evaluate generation quality, the quantum model performs equivalently to its classical counterpart. The modest gains seen in low data regimes behave as regularization, not faithful data expansion. This isn't a dismissal of quantum generative models. It's a call for rigor. The authors emphasize that this negative result is specific to a 4-qubit, depth-to circuit on a single MRI dataset. Larger circuits, alternative encodings, and real NISQ hardware with gate noise and finite shot estimation would likely introduce even more stochasticity, widening the gap rather than closing it. But until we establish controlled, parameter-matched benchmarks with proper statistical testing, claims of quantum advantage in medical image augmentation will remain unverified. If you're working on quantum machine learning or medical AI, I'd highly recommend looking into the full protocol and codebase linked in the description. It's a solid template for future research. Thanks for watching, and I'll see you in the next one.